All right, today we're thinking about how polygons relate to the coordinate plane. So, first of all, if you were placing a polygon on a coordinate plane, you would want to do so in a way that's going to be as convenient to you as possible. So one thing that we would do is we would try to put a vertex, one of those corners of our polygon, maybe on the origin, because that's a really nice point to work with. 0, 0 can provide some very convenient calculations for us. Another thing is to try to use one of the axes as one of the sides to your polygon. Notice right here, that is the base of that triangle. Here, it's the base of that rectangle. Even that rectangle, that rectangle right there, we use the y-axis as the height and the x-axis as the base. Here, we're using the x-axis as the base, and here we're using the y-axis. So that's another convenient thing we can do. Finally, as you notice right here with this rectangle, we might try to make it symmetric to both sides. It looks like whatever length this is right here is the same length going away in that direction. So all of these things can make it convenient if you were placing that shape on the coordinate plane. Here it says triangle ABC has a base of 4 units, a height of 3 units. Angle A is a right angle. Position this triangle on the coordinate plane. Well, if angle A is a right angle, it makes sense for me to make angle A right there at the origin. It says the base is 4 units, so I'm going to make the base go out 4 units. All right, and there's a height of 3 units, so I'm going to stop it right there at 3. And I connect these, and look, I've made a triangle. I'm going to name this ABC on my diagram, but notice once again how I was smart. I mean, I could have put this anywhere, but it just makes it easiest if I use the origin and I use the axes when I can. Here we want to write a proof to show that this is indeed an isosceles triangle. So just having this graph, looking at this, I noticed if this is an isosceles triangle, it looks like this side right here is going to be congruent to that side. And all I need to do in order to show that this is an isosceles triangle is show that we have 2 congruent sides. So I'm going to calculate the distance between these 2 points and the distance between these 2 points over here. Of course, to calculate the distance, it is the difference in our x's squared plus the difference in our y squared. And so this is calculating that side length right there. This gives me 9 plus 4, and so that is the square root of 13. If I do the same thing over here, find the difference in my x's squared plus the difference in my y squared notice once again I get the square root of 13. So since both sides are square root of 13, if 2 sides are the same measure, if they're the same length, then that means they are congruent. So this is, just by doing this, by finding the distance between these points and showing these 2 sides are equal, we've shown that this is definitely an isosceles triangle. Let's take a look here. It says a square has a side length A. Place the square on the coordinate plane and label each vertex with an ordered pair. Okay, so I'm going to put the square right here with a corner on the corner vertex on the origin. I'm going to let it go out A units, and I'm going to go up A units. And if it's a square, then all the sides have to be the same. And so if I am labeling these vertices this is definitely the origin. I'll do this in a different color. This is 0, 0. If I went over A units, that means the x-coordinate is A. I didn't go up any, so the y-coordinate is 0. Here I went over 0 units, and I went up A units. And here it was over A, up A. That fourth vertex has an ordered pair of AA. We've got parallelogram. OPQR, one side length labeled C, assign possible coordinates to the vertices. All right, so I'm going to place again a vertex at the origin. That makes sense to me. One side length is labeled C, so if I go over C units, that looks good right there. No matter what happens, my parallel side, so if I put a parallel side right here, has to have that same side length, because we know parallelograms, the opposite sides are congruent. The opposite sides are also parallel. So I know both of those have to have the same length. They're both going to be C. I'm just going to connect these now to make my parallelogram, and I'm going to assign possible vertices. This, of course, is 0, 0. I went over C, up 0. Here I went over some amount. Right here I went over some amount. I'm going to let that amount be A to get to here. And then I went some amount that I'm going to let this amount be B. So this is a little confusing here probably. Went over A, up B. Because I'm letting these be variables. These are possible coordinates. Over A, up B. That point would be A comma B. Finally, to get to this point, right there, that point, I went over A, the distance A, plus the distance C. A plus C would be my x-coordinate, and then I went up the same amount, B. Notice it went over A, I went over C, I went over A plus C, and then went up B. Finally, assign coordinates to the vertices of isosceles triangle STU with a height of 4 from the vertex. All right, I want this to be STU. I'm going to actually let this be centered at the origin. There's my origin right there, 0, 0. I let it have a height of 4. So I know that vertex has an ordered pair of 0, 4. We can see that. And it went over the same amount on the left and the right, because if I'm going to make those two sides have the same length, if they're going to be isosceles, well, all I have to do is come out the same amount on both sides. I believe that would make sense. It would make two congruent right triangles, meaning the hypotenuses would be congruent. So I went over, I'm going to say A units. I'm going to let that little be A right there. A units. I went over A, I went up none. In this direction, I went over a negative A units, and I went up none. So those would be my possible coordinates. It doesn't matter where we go in each direction here, as long as it's A units over to the right and A units over to the left. All right, here, parallelogram ABCD has vertices A at the origin, B at 3, 0, C at 6, 8, 2, 3, 4, 5, 6, 5, 6, 7, 8. And we want to find the ordered pair for vertex D. All right, we have a fourth point at vertex D. And there's really two ways we could draw this. This is a parallelogram, so I could assume, well, this is parallelogram ABCD, so we have A, we have B, we had point C, so we know it's going in this order A, B, C. And so D must be back in this direction. This must be D in order for this to connect and be a full parallelogram. I know the opposite sides are congruent and parallel, and since AB was a horizontal line, I know that DC is going to be a horizontal line. They are parallel, but I also know they're going to be congruent. So since AB was 3 units, DC must be 3 units. In this point right here, D is the point 3, 8. It's 3 units back to the left of point C. D must be the ordered pair 3, 8. Finally, isosceles triangle XYZ has vertices X at 1, 1, Y at 5, 1. And we want to find an ordered pair for vertex Z. So because this is isosceles, it might help if we kind of highlight right there in the middle between these 2 points. Any point on this line that is not that point right there would make an isosceles triangle. Notice any point we put on this line down here, those 2 are going to be congruent sides. So there, if I let that be the base of my isosceles triangle, that right there would be an isosceles triangle. Those 2 sides would be congruent. I could do a point way up here. Notice how those 2 would be congruent sides if I drew those. As long as our x value is 3, and then it doesn't matter what we let that y value be, any y value, as long as y does not equal 1. Because if we let y be 1, this would form a straight line. We know a straight line is not a triangle. So as long as y doesn't equal 1, you'd be good. 3, 4, 3, 6, 3, comma, negative 71.2. That would form an isosceles triangle. So that would be the easiest way to do that problem.